Thank you for having me. So, today I want to talk about a geometric setup which allows us to extract a lot of non-trivial information about five-dimensional supersymmetric quantum field theories. So, the way it works is that there is a correspondence between Calabi-Yau threefolds, and so there's some geometry on one side, and the physics of the 5D theory on the other side. And so suppose you know some perturbative information about your five-dimensional theory, then you can use this correspondence to translate it onto the geometric side, and it gets converted into some geometric ingredients. So you get a partial list of geometric ingredients, and then you apply some consistency conditions, some geometric consistency conditions, which is often enough to bootstrap it completely into a full geometry. So now you get some new extra ingredients on the geometric side. When you translate them back on the field theory side, you learn some non-perturbative information about a 5D theory. So now you can play around with all this information you have and extract a lot of non-trivial physics that you cannot extract by knowing just the perturbative data of a theory. So in this talk, I will be throughout this talk, I will be in the world of M theory, compactified on a Calabi-Yau threefold, and we will mainly be interested in the intersection theory of this Calabi-Yau threefold. And we will be studying various applications to five-dimensional n equals to 1 quantum field theories. So I want to start my talk by just describing what these applications would be, and then we would study them in detail. So the first application would be the classification of five-dimensional superconformal field theories. Then you can look at gauge theories in 5 dimensions, supersymmetric gauge theories, and you can ask the question, if this gauge theory UV completes into a 5-dimensional superconformal field theory or a 6-dimensional superconformal field theory compactified on a circle. So on the other side, what happens is that suppose you have a 5-dimensional superconformal field theory, then you can perform a mass deformation to go to and after the mass deformation, you obtain a 5-dimensional n equals to 1 gauge theory. This mass deformation is the 1 over g Young-Mills squared of the from the point of view of the gauge theory.
Sorry, Lakshya, can I ask a question at this point?
Yeah, sure.
So did you assume that all the 5-dimensional superconformal field theory can be realized from M theory? Is that the assumption, or?
Yeah, I will. That's an assumption, and there will be lots of justifications throughout the talk. So the Coulomb branch of these 5D CFTs is some abelian gauge theory. So I'm assuming that there is always a Coulomb branch, which leads to an abelian gauge theory. And now this abelian gauge theory is some U1 fields with some matter which has some charges under this U1s. This data is almost equivalent to data of some resolved Calabi-Yau threefold. So you can go back and forth between these two data.
Okay, thank you.
Yeah. Right. So here are some examples of.
Sorry, Lakshya. Excuse me to interrupt. I assume you have in mind local Calabi-Yau threefolds that you're comparing.
Yes.
Okay. Because in your answer to the previous question, you phrased it a little bit as if it was a global threefold. But okay.
No, I'm always working with local Calabi-Yau threefolds.
Okay.
Yeah.
Local means the resolution of some kind of singularity, I assume. What do you mean by local?
Yeah, I mean that it's a non-compact Calabi-Yau threefold if it's a 5D CFT, and so all the relevant data are some complex surfaces and curves which are localized in some reason.
I think what local really means here is that it's some kind of resolution of a singularity. Do you have in mind something more general than that?
Yeah, in some cases it's more general. I want to talk about local pieces of Calabi-Yau threefolds, and this Calabi-Yau threefold can be compact or non-compact, but I want to focus on a local region of it.
Well, all right. I don't want to interrupt you more, but at the end I'm going to ask you for an example that isn't a resolution of a singularity.
So I couldn't hear you.
I don't want to interrupt you more now, But at the end, I will ask you to give an example that isn't a resolution of a singularity.
All right. Right. So some examples of this five-dimensional gauge theories, which can be UV completed, are SU2 with n number of fundamental hypers. And it's known that UV completes into a 5D SCFT if n is less than equal to 7. It UV completes into a 60 SCFT on a circle if n is equal to 8. And this 60 SCFT is known as the E-string theory. And it's expected that if you have more than 8 flavors, then there is no SCFT UV completion. I will also be looking at enhanced flavor symmetries of 5D SCFTs.
When you say that it is known that that it is completed, this is not unique. There might be more ways to
complete it. Yeah, so I have a particular kind of UV completion in mind. So if you are going to mass deform this 5D SCFT, then on the Coulomb branch you are going to observe some sets of BPS particles and the low energy gauge theory. So the low energy theory is just the Coulomb branch of this gauge theory, and the BPS particles can be understood in terms of instantons of this gauge theory.
No, I understand that. My question is, are you implying that there is a unique completion, or do you have in mind, or are you saying that this is one option and there might be others?
There might be others if you allow yourself to add some extra information which is outside the gauge theory, but I expect it to be unique if you do not add any information which cannot be captured in gauge theoretic terms.
I don't understand what that means.
So
for example, the theory of the analog of all these gauge theories is a theory of pions, and the analog of the BPS states would be, say, the skyrmion.
So can you say that again?
An analog of what you said in four-dimensional gauge theory is that instead of the SU2 gauge theories here, you have a theory of pions, and the analog of the BPS states would be a skyrmion. Now, I don't think anybody knows whether there's a unique UV completion of that or not. And I don't know what it means adding more information.
Right. So in this five-dimensional case, what I mean is that suppose you have a UV completion, then the Coulomb branch of this UV complete theory should have the dimension which is the dimension of the Coulomb branch of this gauge theory. This is the kind of UV completion I'm looking for, and it's expected to be unique from M theory. This kind of UV completion. So in some sense, I don't want to add any extra data to the gauge theory. So I could have added some other particles which cannot be described in terms of the gauge theory to produce some new, maybe I could UV complete SU2 into an SU3 first, and then go to the corresponding 5D SCFT, the one unique one that I'm expecting. But I don't want to do that. I want to just directly go. I don't want to add something new. Or in the other direction, you can understand that you do a mass deformation and you land exactly on SU2 and not something more. Does that answer your question, Martin?
Not really, but maybe. Here's an obvious example. Take one of these examples that you discussed and just add a massive hypermultiplet. It is completely decoupled. It satisfies all the requirements you said. It has the Coulomb branch, the BPS states, and so on. There's another decoupled particle.
Yes.
How do you know whether this combined system can be UV completed to something else or not? I don't think we know that.
No, I don't know if it can be UV completed. I'm just saying that I'm looking for certain kind of UV completions here, and I will be describing when this theory can be UV completed without adding some extra stuff like this extra hypers. Without adding anything new to the gauge theory, can it be UV completed?
Are you asking me?
No, I'm just saying this is the question I would be answering.
Okay.
Yeah. So yeah, I will also discuss enhanced flavor symmetries of 5D SCFTs. For example, in the case of SU2 with flavors less than equal to 7, that is when you have a 5D SCFT UV completion. Classically, you can see that there is a symmetry, SO2 and symmetry rotating this hypers. But it's not, and there is a U1 instanton symmetry coming from SU2. So this SO2 and times U1 gets enhanced to En plus 1. This is a well-known fact, and I would like to describe how this can be understood geometrically, and various other examples. Yeah, then we can study dualities between two five-dimensional gauge supersymmetric gauge theories. So what this means is that you have two gauge theories which UV complete into the same 5D or 6D superconformal field theory. Or if you look at it from the point of view of the 5D SCFT, you have a space of mass deformations, and choosing one of the mass deformation takes you to one of the gauge theories, and choosing another mass deformation takes you to the other gauge theory. Then, so here is an example. The example is sp2 gauge theory with n fundamental hypers, and is known to be dual to SU3 gauge theory with n fundamental hypers with a particular choice of Chern-Simons level. As long as n and these two UV complete to 5D SCFT, if n is less than 9, and if n is equal to 10, they UV complete to a 60 SCFT on a circle. This 60 SCFT can be given a more concrete description if you move on to the tensor branch of this 60 SCFT, where it becomes a 6-dimensional SP1 gauge theory carrying 10 fundamental hypers in 6 dimensions. And then an extension of this allows you to also understand T dualities between 6-dimensional 1,0 little string theories, where a well-known example is the T duality between 2,0 and 1,1 little string theories, which are the world volume theories of NS5 branes in type 2A and type 2B respectively. And you know that they get exchanged under T duality. This 1,1 little string theory can be given a more concrete description as maximally supersymmetric gauge theory in 6 dimensions if you, on the tensor branch. Right, so now I'm going to move to the main part of my talk and describe all of these applications and the geometric setup that I have in mind. So I'm going to look at some local regions inside some Calabi-Yau threefold. This Calabi-Yau threefold might be compact or non-compact, but I want things to be smooth. I don't want any singularities. And so here is a cartoon of this Calabi-Yau threefold, a local region inside this Calabi-Yau threefold. And the lines here are representing some complex surfaces. And these complex surfaces are then intersecting with each other in some fashion. So these are the kind of mathematical objects I want to study. Now, if you have this local region, if you focus on this local region, then you can establish a correspondence between such a local region and 5-dimensional n equals to 1 abelian gauge theories. So the way it works is that if you take each on a complex surface Si, you compactify the M theory 3 form on it, you get a U1 gauge field corresponding to each surface. Right, and the matter is encoded inside various complex curves, the way they intersect these complex surfaces. So now, if you want this 5D n equals to 1 abelian gauge theory to arise on the Coulomb branch of some 5-dimensional SCFT, then it imposes a certain structure on this local region, on this set of surfaces. This structure can be thought of as a shrinkability structure. So what it means is that you should be able to contract all the compact complex surfaces and the compact complex curves in this region to a 0 size simultaneously at some point in the moduli space. So if this is possible, then that point in the moduli space becomes the conformal point of the 5D SCFT, and then you obtain a singularity at that point. And this local region can be thought of as a resolution of the singularity, which corresponds to moving on the Coulomb branch of this 5D SCFT. Right. So this is a structure on this geometry. Shrinkability is the structure on this geometry that you need to impose to obtain 5D SCFT. Now I want to these abelian gauge theories can also be obtained on the Coulomb branch of a non-abelian gauge theory in 5 dimensions. And there should be some corresponding structure on this set of complex surfaces, which tells you if it is coming from a non-abelian gauge theory. This structure is that each of these surfaces should be a P1 fibration. So let me discuss this correspondence between non-abelian gauge theories and P1 fibered surfaces in more detail. So let's say that let me call each fiber inside each surface Si as Fi. Wrapping M2 brane on this fiber produces the W boson corresponding to this motion onto the Coulomb branch. The volume of this fiber can be identified as the mass of the W boson. So if you want to go to the origin of the Coulomb branch, you want to send the mass of W bosons to 0, so which means contracting these fibers. Right, and so these P1 fibered surfaces can be understood in terms of Hirzebruch surfaces and their blowups. So I want to study Hirzebruch surfaces and their blowups. So the Hirzebruch surfaces are P1 fibrations over P1. So they are not the most general P1 fibered surfaces, but if you want more general P1 fibered surfaces where the base is some higher genus curve, then you can produce them by blowing up these Hirzebruch surfaces and gluing them with each other by self-intersecting with them. So in this way, you can change the genus of the base curve. So essentially, the whole theory is about Hirzebruch surfaces and the blowups. Now, let me call this base P1 as EI from now on. And if you wrap M2 brane on this, you obtain an instanton for the non-abelian gauge theory, whose volume can be identified as 1 over G Young squared. So if you want to decouple your gauge group, you want to decompactify the base. Okay. This non-abelian gauge theory can be described completely in terms of the data of a gauge algebra and some matter content. So there should be something on the geometry side which captures the gauge algebra and the matter content. So let me first describe how to capture the gauge algebra. So the gauge algebra is captured in an intersection matrix. This intersection matrix is the intersection between the fibers and the surfaces with a negative sign, and this matrix should be identified with the Cartan matrix of the non-abelian gauge algebra. The reason this holds true is because these surfaces are giving rise to U1 gauge fields. They can be identified as the co-roots. The fibers can be, because they're giving rise to W bosons, can be identified as roots. So there is this intersection matrix is some pairing between roots and co-roots. So it should be proportional to Cartan matrix, and the sign can be determined to be a negative sign, as we will soon see. Now, how do you add matter to this setup? Which you can probably guess now, because some complex curves inside this geometry are the roots. Some other complex curves inside this geometry should act as weights of the representations in which the matter is transforming. So, and you need to have blowups to produce matter content. So you take some general curve C, which is some linear combination of blowups and fibers. Then if you look at minus C dot Sj, then this produces Dynkin coefficients for you for the representation in which the matter content is transforming. In this way, if you're given a geometry like this, such that all the surfaces are P1 fibered, and such that the intersection matrix associated to the geometry is actually Cartan matrix of a finite Lie algebra, then you can associate to it a 5-dimensional n equals to 1 non-abelian gauge theory. Or if you start with a 5-dimensional n equals to 1 non-abelian gauge theory with some matter content, you can write down such a local geometry corresponding to it. Right. So to study the 5-dimensional theories, hello. Yeah. So to study these 5-dimensional theories, we essentially want to understand intersection theory of these inside this Calabi-Yau 3. This intersection theory will reduce to the intersection theory of Hirzebruch surfaces. So I want to review it briefly. So let's take the base P1. It will have some self-intersection. Let's call it minus n. The fiber P1 is a fiber. It can be moved around without intersecting itself. So its self-intersection is 0. And the base and fiber intersect each other at one point. So they have a +1 intersection. And such a surface is I will denote it by Fn, a Hirzebruch surface of degree n, where n corresponds to this minus n over here. And then we can add some blow-ups to it. So x's will denote some blow-ups, which are -1 curves, which are P1. So they have self-intersection -1. Two different blow-ups will not have any self-intersection, and the blow-ups are not going to intersect any of these curves. So this might be a little confusing, because in my notation I'm always working with total transforms. So what I mean is that when I do a blow-up, then the full curve, including the blow-up, is what I'm going to call as the new E. So if I blow up E, then I obtain a curve E minus x, which is the proper transform, and the full transform is actually E minus x plus x, which I will still denote as E. So in this sense, the blow-ups do not intersect each other, and the blow-ups do not intersect E and F. And if we have B blow-ups, I'm going to put a superscript B on the Hirzebruch surface. The genus of E, F, and all the blow-ups is 0. They are all P1s. And now a general curve inside this geometry can be written as a linear combination of E and F minus some blow-ups. So minus sign appears because these blow-ups are hitting this linear combination of E and F. Or you can have some blow-up minus some blow-ups when a blow-up hits some other blow-up. Right. So this is the intersection theory of a single complex surfaces. But now we have multiple complex surfaces intersecting each other. So let's look at one such intersection. So here we have an S1 and another surface S2 intersecting it transversely. Intersection is going to happen along a complex curve C. So if you restrict this C to S1, you obtain some curve C1 inside S1. If you restrict this curve C to S2, you obtain some curve C2 inside S2. So another way to describe this intersection is to say that you're taking C1 inside S1 and C2 inside S2 and you're gluing them together. And now this gluing better satisfies some consistency condition for you to obtain, still obtain a Calabi-Yau. For the ambient space to still remain a Calabi-Yau. So first of all, there's just a topological condition. The genus of C1 and C2 should match, and let's call this genus to be G. For the ambient space to be Calabi-Yau, the one necessary condition is that the sum of self-intersections of these two curves inside their respective surfaces should be 2G minus 2. So this will be a very important consistency condition that we will use throughout this talk. Right, so this is all the intersection theory knowledge that we needed, and now we can already start producing some results. So let me look at some very simple examples and describe how this machinery works. So here I'm taking a surface F2 and another surface F0, and then I'm gluing them together, so they're intersecting each other with a single intersection, which is described by the gluing that the E curve inside F2 is glued to E curve inside F0. And now we need to check, so both of them are P1, so this topological condition is satisfied, and the Calabi-Yau condition can be checked to be satisfied. The self-intersection of this E curve is -2, self-intersection of this E curve is 0, and this sum is -2, and the genus was 0. So this condition is satisfied. So this is the consistent geometry. And now we want to see what is the gauge theory corresponding to it. So first, let's compute the gauge algebra. And for that, we need to compute this intersection matrix minus fi dot sj. And let's look at the diagonal entry first. So the diagonal entry is fi dot si, which can be which is equal to the canonical class of the surface si dotted with intersected with fi. And now using adjunction formula, you can describe this intersection in terms of the genus of f and the self-intersection of f. And if you put the numbers together, you find -2. So this fixes the sign to be minus because Cartan matrix must have a diagonal entry to be +2. So you find that all the diagonal entries have to be +2. And now we need to compute the off-diagonal entries. So let's compute the off-diagonal entry where and let me call this as the first surface and this as the second surface. So I want to compute the first fiber intersected with the second surface. Since the second surface intersects the first surface only along this curve E inside the first surface, the first fiber is going to intersect the second surface along only along the curve E inside the first surface. So we want to compute f dot E inside this first surface, which we know to be +1. So we see that the off-diagonal entry must be -1, and same for the other off-diagonal entry. This gives you a Cartan matrix of SU3. And now there are no blow-ups. So this geometry corresponds to an SU3 pure gauge theory in 5 dimensions. And there is a Chern-Simons level that you can associate to it, which I'm not going to get into details of that, but it can be computed to be -1. So this Chern-Simons level is computed using the prepotential of the 5D theory, which can be computed geometrically using the triple intersection numbers of the surfaces, which also reduce to the intersection theory of complex surfaces. So the whole data so far is just about the intersection theory of complex surfaces. So this was one example. Now I want to consider a slightly more interesting and slightly more complicated example, where I'm taking a surface F0 and a surface F6, such that I'm gluing 2E plus F inside F0 to E curve inside F6. So first of all, to check the Calabi-Yau condition, you can compute the self-intersection of 2E plus F to be +4. So +4 minus 6 is -2. It's a consistent Calabi-Yau threefold. It's a consistent geometry. And so we want to see now what is the gauge theory corresponding to it. You compute the intersection matrix, but now the off-diagonal entries are on this side. The fiber is going to intersect 2E plus F, which it is in particular because F squared is 0, it's going to intersect 2E, so it's going to give a -2. One of the off-diagonal entries is going to be -2. The other one is just like before, it's going to be -1. This is the Cartan matrix corresponding to an SP2 gauge theory, to an SP2 algebra. And since you have no blow-ups, you expect a pure SP2 gauge theory. Okay, so now the interesting thing happens because you have an F0 here. In F0, E squared is 0. So it means that E is another P1 fiber. So this means that F0 is actually just a trivial fibration P1 times P1. And it does not matter which one you call as E and which curve you call as F. So I can exchange the role of E and F. This does not change my geometry. So let me do that. Let me exchange E and F. Then I can write my geometry like this, where I have E plus 2F being glued to E. And now if you compute the Cartan matrix, the off-diagonal entry is going to be -1 instead of -2. So you obtain an SU3, pure SU3 gauge theory. So the same geometry describes for your pure sp2 gas theory and a pure SU3 gas theory, depending on how you choose your P1 fibers. This means that there is a duality between these two theories. So if there is a UV completion, if these surfaces can be contracted, can be completely shrunk, then there should be two different ways of expanding the fibers, giving fibers a volume to land onto Coulomb branch of sp2 or Coulomb branch of SU3. And here the Chern-Simons level is actually -5. So you obtain a duality between pure sp2 and pure SU3 with Chern-Simons level -5. This is one of the dualities I discussed in the starting of my talk.
Can you clarify exactly what you mean by a duality here?
So I mean that if these have a UV completion, so in this case there is a UV completion to a 5D SCFT, then there exists two different mass deformations of this 5D SCFT. Having one mass deformation leads you to an SU3, pure SU3 non-abelian gas theory, and turning on the other mass deformation leads you to a pure sp2, a non-abelian gas theory.
But in what sense is it a duality?
This is what my definition of a duality, that they have the same UV completion in 5 dimensions, because yeah, just like in 3 dimensions you can have IR dualities. The different theories, different SCFTs can lead to the same theory in the IR. Here there is it's a UV duality in a sense.
So if I take some multi-critical point that under two different deformations flows to two different critical points, would you say that the two critical points are dual?
I mean, in 5 dimensions, I'm calling them to be dual because, yeah.
So imagine I take some phi to the n field theory, say, in 2 dimensions, and n is large, and I deform it by phi to the m or by phi to the k to find two different lower energy, lower minimal models. Would this definition, under this definition, you would call them dual to each other? Because they're both quote unquote completed to the same multicritical point.
No, I mean, you should not be calling them dual in the example you're considering, but here it's a very special situation because you're looking at supersymmetric mass deformations. So you have two different 5D gauge theories, and you do not expect, you're a priori not expecting them to have the same UV completion. You would think that they don't have the same UV completion. And if they do, then it's sort of surprising.
I don't see the difference, because if I take, say, phi cube with a deformation, an irrelevant deformation, and phi to the 5th with irrelevant deformation,
no,
then
these
you can
are
probably combine.
I'm considering.
Sorry?
Here in 5 dimensions, I'm considering relevant mass deformations. So I have there are two non-abelian gauge theories at low energies I have. One of them is sp2, one of them is SU3. I won't think that they are going to be actually UV completed into the same 5D SCFT. And if it turns out that they can be UV completed into the same 5D SCFT, then it's surprising. The 5D SCFT has a rank 2 Coulomb branch, which is the same as the rank of these Coulomb branches. So I have not done something very drastic. I have not added a huge number of degrees of freedom to these theories to concoct this duality. It's sort of a natural duality. Right. So these two, this is an example of the duality I consider I talked about in the starting of my talk, where we have sp2 with n flavors and su3 with n flavors. So we have been able to obtain when the duality when n is equal to 0. So can we obtain the duality when you have some number of flavors? So for this, I need to tell you how to add matter to gas theories. So far, we have only looked at pure gas theories. So adding matter to these theories from the geometric point of view is very simple. You simply add some blow-ups on these surfaces. So if I look at this geometry for pure sp2 gauge theory, and I'm reproducing it here, and I'm adding n blow-ups on f6, then you want to see what is the representation in the gauge theory which is induced by these blow-ups. And for that, you need to compute the intersection of the blow-up with the surfaces. And if you compute that, you find that you find Dynkin coefficients for the highest weight of fundamental of sp2. So adding one blow-up adds one fundamental of sp2 into your 5D theory, and adding n blow-ups adds n fundamentals. So this geometry is describing sp2 gauge theory with n fundamentals. And now you can again exchange E and F on the left surface, and you obtain that sp2 with n flavors is dual to su3 with n flavors, with some choices of Chern-Simons level, which can be figured out to be minus 5 plus n over 2. So we obtain a duality for general n. And so far, I have not discussed shrinkability criteria. So n can be anything, n can be above 10 as well. As we saw in the starting, if n is less than equal to 9, then they have a UV completion into 5D SCFT. That means that this geometry, this local region can be embedded inside a non-compact Calabi-Yau threefold, where the only compact structure is captured by this local region of this non-compact Calabi-Yau threefold. When n is equal to 10, we expect it to UV complete to a 6-dimensional SCFT on a circle, where the Calabi-Yau threefold is not completely shrinkable, but you obtain a T2 fibration, as we will soon see. So except the T2, everything else can be shrunk. And if it's above, if n is more than 10, then it's not clear because there is no SCFT UV completion you expect. You do not expect it to be embeddable into a non-compact Calabi-Yau threefold, but maybe it could be possible that it can be embedded into some compact Calabi-Yau threefold. That maybe for n equals to 11, this duality might be relevant in the context of 5D supergravities. But we are not studying that problem, so I leave it open. Whether this local region of a Calabi-Yau threefold can be embedded into some consistent compact or non-compact Calabi-Yau threefold. So and for n more than 10, all these dualities should be viewed with suspicion. Yes.
Well, you described the surfaces and the intersection, but are you also going to describe the ambient Calabi-Yau, or is it something trivial?
Yeah, it's just the canonical bundle over this set of surfaces.
But then you have to glue the two canonical bundles over two surfaces, and that's the condition that you gave us.
This gluing is fixed by Calabi-Yau, if you demand your ambient space to be Calabi-Yau.
Well, that's what I'm asking. How do you construct Calabi-Yau? You have canonical bundle over one surface, canonical bundle over another. Now you glue them somehow.
Yeah. So so now you have to obey this condition. The self-intersection should be this. The sum of self-intersection should be 2G minus 2.
And you claim that this is sufficient.
Yes, this is sufficient because it's a transverse intersection. So one of the self-intersections tells you the bundle in one of the directions, and one of the self-intersection tells you the order of the bundle in the other direction.
Well, I understood that you claim that you can do it for any collection of surfaces such that the pairwise intersections satisfy this. Is that the claim?
Can you repeat it?
You started with a collection of surfaces, and now you describe pairwise intersection of each of them. Are you claiming that for any collection of surfaces such that pairwise intersections satisfy this condition, there is a local Calabi-Yau?
Yeah, there is at least a local region of a Calabi-Yau. I don't know if it can be extended to infinite.
Which contains all of these surfaces.
Yes, yes. So I mean that you might sometimes have to cut it off at some distance. So you take the bundle, you at least get this. You try to construct this. You know how to glue the canonical bundles together. And then after that, there might be some singularity at some finite distance, some extra singularity which you were not expecting, or some extra compact curves. And so you might have to cut it off for for n greater than 10 in these examples, for instance. So, but if n is less than equal to 10, then I expect that it can fully go without any additional singularities.
No, my question is not about n, but the number of surfaces. Let's say I have 15 surfaces, and all pairwise intersections satisfy your condition. Then you would say that there's Calabi-Yau that contains all 15 of them.
Yes, yeah. So that would be like SU16. Yeah. So you suppose S1 intersects S2, then S2 intersects S3, and so on up to S14, S15. Then it would be an SU16.
Suppose all of them intersect.
Sorry?
Suppose all of them intersect, any pair of them intersects.
All of them intersect, then it would be not a gauge theory. It will be the intersection matrix will be more complicated than a.
That's what I'm asking. So you have a criterion for when there is a Calabi-Yau which contains the surfaces that you want?
Yeah, in some cases it should be, when I will discuss shrinkability criteria, I will come to, for in some cases I know when they should be embeddable into a consistent Calabi-Yau 3-foot. Yeah. Right. So we have discovered this duality between SP2 and SU3 gauge theories with n number of fundamental flavors. And now, this was just one example. In general, the dualities work as follows. You construct some geometry corresponding to some gauge theory. Then you can apply some isomorphisms to it, and then change your, maybe you can go from a gauge theory like Cartan matrix to a non-gauge theory like Cartan matrix. And then you do some flops on it. Then you can perform a sequence of these isomorphisms and flops such that you go from a finite Cartan matrix to another finite Cartan matrix. So here Aij goes to A prime Ij, and then the curves, the blow-ups are going to arrange from weights for representations of the first gauge algebra into the weights for representations of the second gauge algebra. So in this way, you can obtain an arbitrary duality between the starting gauge theory and an ending gauge theory. Okay, right. So now I want to discuss the situation when n is equal to 10. Because for n is equal to 10, we expect it to lift not to a 5D SCFT, but rather to a 6D SCFT compactified on a circle. So can we see something interesting happening in the geometry for this case? So for n equals to 10, this is the geometry on the left-hand side. Then there's an isomorphism I can apply on the right surface and rewrite this geometry as follows, where I have F0, the left surface is left as it is, and the right surface is now an F0 with 10 blowups, and I'm writing the curve E plus 2F minus summation xi. I'm using this curve as the gluing curve. You can check that the self-intersection of this is actually -6, which is the self-intersection of the E curve here. So this can be an isomorphism. I claim this is an isomorphism. And now you interchange E and F because you have another F0. So you obtain 2E plus F minus summation xi. So the starting geometry can actually be written in terms of two F0s, such that the two gluing curves on both sides involve a 2E. So now the Cartan matrix associated to it is going to have both the off-diagonal entries to be -2. And this is the Cartan matrix for an affine SU2. So for all the affine Lie algebras throughout this talk, I'm going to insert a superscript 1. So now this is interesting because you know that affine SU2 cannot appear as a gauge algebra because you want the kinetic matrix to be positive definite for a gauge theory, and the kinetic matrix corresponding to it, which is given by the Killing form, is going to be positive semi-definite. So this should not be you should not be able to contract the both of these fibers to go on to a origin of the Coulomb branch of some affine SU2 gauge theory. So here you should, what you can do is you can contract, say, one of the fibers to go to an SU2 times a U1 for this, or you can contract the other fiber to go to an SU2 on the a U1 times an SU2. But you cannot contract both of them simultaneously. So you're already seeing that you're losing some shrinkability in your geometry. The physics tells you that it should not become it should not be shrinkable, Calabi-Yau threefold. Okay, so we can understand it more mathematically, the loss of shrinkability. To do that, let's look at the fibers, the two fibers that we have. They intersect each other. They form a diagram like this, where the two fibers are intersecting at 2 points. And this is a familiar diagram for a Kodaira I2 fiber. So what this means is that your geometry has a T2 fibration, where at the location of the surfaces, the T2 fiber degenerates to an I2 Kodaira fiber. What it means is that you have a T2 and you take a particular cycle, let's say A cycle, and you take 2 copies of it and shrink them. You pinch the T2. This is how it looks like in real space. So you have discovered a Kodaira I2 fiber in your geometry, which means that the geometry is T2 fiber, and that means that so it's an elliptic. Your Calabi-Yau threefold is an elliptic fibration, and now there is a well-known criterion due to Grauert for shrinkability, which guarantees that if you have this a T2 fiber in your Calabi-Yau threefold, then it cannot be shrunk simultaneously to a point with the rest of the geometry. So it's not a shrinkable Calabi-Yau threefold, and so it should not be a 5D SCFT. Right. So what we have now obtained is an elliptically fibered Calabi-Yau threefold, with, let's say, the base of this it is B. And now you recall the duality between M theory and F theory. F theory is always formulated on elliptically fibered Calabi-Yau threefolds, and now you have M theory compactified on elliptically fibered Calabi-Yau threefold. And in F theory, the fiber has 0 volume. In M theory, there is some finite volume to the fiber. So the duality between F theory and M theory says that if you put the F theory on a circle, then the radius of that circle tells you the 1 over the radius of the circle tells you the volume of the fiber in M theory. So using this duality, you know that the Calabi-Yau threefold that now you have constructed in M theory now you can take it to F theory. So you're describing some 6-dimensional theory compactified on a circle. And in this duality, it is known that if you have an affine SU2 Kodaira I2 fiber, if your T2 fiber degenerates to a Kodaira I2 fiber over some curve in the base, then on that curve you have a 2D7 branes wrapping it. So you obtain an SU2 gauge theory in 6 dimensions. So this geometry is actually describing an SU2 gauge theory in 6 dimensions, compactified on a circle, which appears as an affine SU2 in the M theory geometry. So the general correspondence is like this: if you obtain an affine intersection matrix in your geometry, which I'm writing as affine gauge algebra, then this should be thought of as a 6-dimensional gauge theory on a circle. And it's known that 6-dimensional gauge theories can be obtained on the tensor branch of 60 SCFTs, many 6-dimensional gauge theories. This was for a general 6-dimensional gauge theory, but a subset of them can be obtained on the tensor branch of 60 SCFTs. So you need some sort of condition on this elliptically fibered Calabi-Yau threefold to know when the gauge theory is shrinkable. And this condition, so when the gauge theory actually comes from a 60 SCFT, and this condition is known to be that your base, the compact curves in the base should be simultaneously shrinkable to a point. Okay, so far in our discussion, we have concluded that 5D SP2 with 10 flavors is lifts to has the same UV completion as 5DSU3 with 10 flavors and Chern-Simons level 0, which I'm calling as duality between these two 5D gauge theories. And the UV completion is actually a 6-dimensional SU2 gauge theory with 10 flavors. And this is known to UV complete into an, this is known to be tensor branch theory of a 6-dimensional SCFT. Okay, so using this sort of manipulations, we can have many possibilities. We have seen that if you have a finite, if your intersection matrix is for a finite Lie algebra, you can perform some isomorphisms and go to intersection matrix for a finite Lie algebra. And this is what I'm referring to as duality of 5D gauge theories. So in this way, you can discover duality of 5D gauge theories. We also discussed that if you have a finite Lie algebra intersection matrix, then you can go to an affine Lie algebra intersection matrix. And in this case, the physical interpretation is that the 5D gauge theory you have on the left-hand side actually descends from a 60 gauge theory compactified on a circle whose gauge algebra is encoded in this affine Lie algebra. And now an extension of this is that you start with an affine intersection matrix, and by performing isomorphisms, you go to another affine intersection matrix. Then this means that you have two 6-dimensional gauge theories compactified on S1, the one on the left hand side and on the right hand side, and then they become dual to each other after compactifying on circle. So this hints that these two 60 gauge theories have a T duality. So you expect these 60 gauge theories on the left hand side and right hand side to arise on the tensor branch of 6-dimensional little string theories. And this turns out to be true in all examples. Right, so far I have discussed some of the applications which are about the dualities, T dualities, and UV completions of 5D gauge theories, 5D SCFTs, 5D gauge theories. Now I want to shift gears and start talking about when these local pieces, geometric pieces, are actually shrinkable. And so they can be embedded inside some non-compact Calabi-Yau threefold. And this will also tie up with the classification of 5D SCFTs, because shrinkable Calabi-Yau threefolds correspond to 5D SCFTs. So shrinkability can be formulated in terms of some positivity condition on the intersection theory. We already saw an example of this here. Right, so when we were discussing this SU2 gauge theory in 6 dimension, here what happens is that the curve in the base is actually a -1 curve. So it's a negative definite, has the base has a negative definite intersection pairing, and in this case it should be contractible. So it indeed UV completes into a 60 SCFT. So in the Calabi-Yau threefold case, when you have a 3-dimensional Calabi-Yau threefold, there is some positivity condition on the intersections between surfaces and curves. So I'm not going to discuss these positivity conditions. They say basically that the curve should have positive volumes, and the surfaces should have positive volume at some point in the Coulomb branch. So now, right, so there are these positivity conditions. And now suppose you are interested in classifying all such geometries which satisfy these positivity conditions, whose intersection theory satisfies these positivity conditions, then one algorithm would be to manually search for all the Calabi-Yau threefolds. So to just write down a geometry, a consistent geometry, and then check whether the intersection theory is positive or not. But then this is a very complex algorithm. Now a smarter algorithm so I will first describe the algorithm, is to use the F theory classification of 60 SCFTs to produce Calabi-Yau threefolds which satisfy these positivity conditions. And this is a much easier problem to tackle. However, I should caution that this does not lead to all of the, this algorithm does not capture all of the shrinkable Calabi-Yau three-folds. It leaves some exceptional cases out, which I will discuss later. So let me first discuss this algorithm. So you start with some classification of 60 SCFTs, which you believe to be complete due to various reasons. And in this classification, one natural data which is included is the tensor branch data of this 60 SCFT. On the tensor branch, each 60 SCFT becomes some 60 gauge theory. So you have a set of some 60 gauge algebras, a supersymmetric gauge theory. So you have some 60 gauge algebras and some matter content. And now you want to put this on a circle. Now, once you put this on a circle, we have seen that each of the 60 gauge algebra would become some affine gauge algebra, and then you will obtain an elliptic fibration. So you can convert this data of 60 gauge algebras and matter content into an elliptically fibered Calabi-Yau threefold of the form we have been discussing with an affine gauge algebra. And now I want to take this Calabi-Yau threefolds and call them as and think of them as some parent Calabi-Yau threefolds. So these will be the starting points for producing shrinkable Calabi-Yau threefolds. And these should be thought of as sitting at the edge of shrinkability. So they do not satisfy shrinkability criteria because they have a T2, but that is all the culprit. The base satisfies the shrinkability criteria. And now I want to find from them some Calabi-Yau threefolds which are totally shrinkable. So I want to manipulate this T2. I want to remove some piece out of this T2, which can be done using a blowdown. So what it means is that we have this T2 which gets degenerated into a bunch of P1s over various locations, and I want to remove one of these P1s out. I want to blow it down. So this blowdown is going to destroy the T2 fibration, and it's going to preserve the number of compact surfaces. I'm remarking this for some future development. So now you have destroyed the culprit to the shrinkability, which is the T2 fiber. So you're not guaranteed to land onto a Calabi-Yau threefold, which is shrinkable. So the construction that I described by gluing the canonical bundles together, here you expect it to complete, to be complete, to actually give you a non-compact Calabi-Yau threefold without any more subtleties in these cases. So you're guaranteed to have shrinkability, and then these descendant Calabi-Yau threefolds can be identified as 5D SCFTs. So the structure so far is that you have some number of parent Calabi-Yau threefolds, then you can blow them down in all sorts of fashions and obtain, for each parent Calabi-Yau threefold, you obtain a set of descendant Calabi-Yau threefolds. And then combining all these sets of descendant Calabi-Yau threefolds, you obtain a huge class of 5D SCFTs. So using this algorithm, we have obtained a huge class of 5D SCFTs, which have been classified as descendants of 60 SCFTs. And the natural question to ask is that, is this classification complete? And the answer to this is no. So I'm going to describe an example, a counterexample of example of a 5D SCFT, which does not fall into this classification. So this example is a 5D gauge theory, which has F4 gauge algebra and three hypers in the 26-dimensional representation of F4. This is known to satisfy shrinkability. So the Calabi-Yau threefold corresponding to it is known to satisfy shrinkability. So it should be a 5D SCFT. And now the question is, can I blow? Okay, so the question is, does it come from the blowdown of some other Calabi-Yau threefold, which is either shrinkable or sitting at the edge of shrinkability, which is an elliptically fibered one? So in the inverse direction, I'm asking the question, if I blow it up, so I'm going to do some arbitrary blow up on the Calabi-Yau threefold corresponding to this gauge theory. And as we have seen that doing a blow up into a Calabi-Yau threefold corresponding to a gauge theory simply adds a hyper in some representation of the gauge algebra. So I'm going to obtain a Calabi-Yau threefold for F4 plus 3F plus some other representation R. And it's known that all such Calabi-Yau threefolds are not shrinkable. So you can see that this 5D SCFT does not it does not fall into this classification huge set of 5D SCFTs that I just described. And there are a few such exceptional cases. So if you look at the set of gauge 5D gauge theories with simple gauge algebras, then you are able to find some counterexamples like this. One of them is F4 plus 3F. And so then you can find some E6 and E7 examples as well. But then there are few of them. But all of these cases can actually be produced from elliptically fibered Calabi-Yau three-folds, using a different operation, which is not a blow-down operation. So in this example, you have F4 plus 3F. This can actually be obtained from a 6-dimensional F4 plus 3F. This was a 5-dimensional F4 plus 3F gauge theory. If you take a 6-dimensional F4 plus 3F gauge theory and put it on a circle, then you are going to obtain a geometry whose intersection matrix gives you an affine F4. So it has one extra surface than this geometry because it has one extra node in its Dynkin diagram. So there is no transition from this 6D F4 plus 3F to 5D F4 plus 3F because of a blow down kind, because the blow down preserves the number of compact surfaces, as I remarked. So here I'm going to remove one surface. The way I do it is that this F4 plus 6-dimensional geometry corresponding to 6-dimensional F4 plus 3F can actually be written after doing some manipulations as a geometry corresponding to 5-dimensional F4 plus 3F, which has an SU2, a non-perturbative SU2 instanton flavor symmetry, and you gauge this SU2 symmetry. So there is some gauging by an SU2 instanton. And now taking the Yang-Mills coupling of this SU2 instanton to 0 removes this, decompactifies the surface for this SU2, and you obtain the geometry for F4 plus 3F. So so far we have looked at two ways of producing 5D SCFTs or of producing shrinkable Calabi-Yau three-folds. The first of them is a blow down, starting from an elliptically fibered Calabi-Yau three-fold, and the other one is a decoupling of a surface starting from an elliptically fibered Calabi-Yau three-fold. The blow down can be thought of as removing a curve from the Calabi-Yau three-fold, and decoupling can be thought of as removing a surface from the Calabi-Yau three-fold. And now, if you wrap as we discussed, if you wrap an M2 brane on a curve, on a compact curve inside a Calabi-Yau three-fold, then you obtain a BPS particle in the 5D theory. So the first kind of RG flow corresponds to integrating out a BPS particle from your 5D theory. The second kind of example, if you wrap an M5 brane on a compact surface in your Calabi-Yau three-fold, you obtain a BPS string in the 5D theory. So the second kind of RG flow can be understood as integrating out a BPS string from a 5D theory. So, and using these two, we have seen that we can produce almost everything. We can for instance produce all of the simple gauge, all of the 5D gauge theories with a simple gauge algebra, which are expected to be UV completed into 5D and 6D SCFTs, into 5D SCFTs. So based on this evidence, now I can provide a conjecture for the classification. According to the conjecture, the set of 5D SCFTs should be obtainable by integrating out BPS particles and strings from 60 SCFTs compactified on a circle. Where here 60 SCFTs, I'm assuming that they have a full classification in F theory. Mathematically, this states that all the shrinkable Calabi-Yau three-fold should be obtainable by removing curves and surfaces from elliptically fibered Calabi-Yau three-folds such that their base is shrinkable. And these are, you can identify this set with the set of 60 SCFTs by F theory. So as I described, that the evidence for this conjecture is the best evidence so far we have is by looking at 5-dimensional gauge theories with simple gauge algebra, which are expected to UV complete to 5D SCFT. because they satisfy some necessary conditions, studied by Jefferson, Kim, Bafa, and Zafrir in 2017. And these theories can be divided into three classes. First of them, which is like the generic case, is the ones for which the Calabi-Yau threefold is known to be shrinkable, and they all lie inside the above classification, in this conjectural classification. Then the second set is the set of theories which are known to be non-shrinkable, so they do not satisfy all the necessary criteria, only some of them, and they do not, of course, they do not lie inside the above classification, because the above classification should only produce consistent 5DS CFTs. And then there is a handful of these theories, some 4 or 5 of them, for which the fate is not known. So, so it's consistent so far. Right. So if the conjecture is true, then we have seen, then according to this conjecture, all the 5DS CFTs should fall into two classes. In the first class, we have 5DS CFTs, which can be obtained from 6DS CFTs by integrating out BPS particles alone and no BPS strings. This is the generic case of the classification. It includes lots of infinite families of theories. Then there is a second case in which 5DS CFTs are obtained from 6DS CFTs, but you need to integrate out some BPS strings as well during the RG flow. And these are some handful of exceptional cases of this classification. And the conjecture states that these two cases should be the full classification. Right, so now this finishes my discussion about the classification of 5DS CFTs. And now I'm going to switch gears and discuss enhanced flavor symmetries. And I should caution that this method only works for the first kind of theories, which is for the generic case, where you can obtain 5DS CFT from 6DS CFT by integrating out BPS particles alone. And okay, so to prepare for it, I need to discuss some 6-dimensional Q-word gauge theories. So suppose you have some Q-word in 6 dimensions with G1 gauge algebra and another gauge algebra G2 with some matter content transforming in both simultaneously under both of them. Now you put this theory on a circle, then you know that you should be able to describe the system in terms of a geometry carrying a local region which contains affine surfaces intersecting in the form of affine G1, and another local region which contains surfaces intersecting in the form of affine G2, which then intersect with each other, these two sets of surfaces, according to what the matter content of the 6D theory is. So here we have some Hirzebruch surfaces for affine G1, Hirzebruch surfaces for affine G2, which intersect each other. Right. So now to go from such a Q-word gauge theory to the situation where you have a non-Q-word theory, let's say G1 with a global symmetry, with a flavor symmetry which is G2, you can simply turn off the Yang-Mills coupling for G2. So you put it on a circle. What does it mean? It means that in the geometry, you have this collection of surfaces describing compact surfaces describing affine G2 side of the theory, and the base curves, which are the E curves inside this, they were the instantons for this G2. So their volume was 1 over G Yang-Mills. So what you want to do is you want to completely decompactify these E curves. So if you know such a compact geometry, by decompactifying the E curves, you can obtain a geometry in which you have a collection of compact surfaces describing the dynamical G1 part of the theory, and a collection of non-compact surfaces which describes the flavor symmetry, the affine G2 flavor symmetry. Right. So yeah, these NG2 are P1 fibered non-compact surfaces. And now in the first class of theories, you want to do some blowdowns on this set, on this compact set. performing these blowdowns is going to affect the set of non-compact surfaces. And after the blowdown, you will get the non-compact surfaces will organize in some other fashion. And this new set of non-compact surfaces will tell you what the flavor symmetry for the 5D SCFT is. So let's do an example, a simple example. Consider that you have a 6-dimensional E-string theory. This is known to have E8 flavor symmetry in 6 dimensions. Now, once you put it on a circle, I told you earlier that E-string can be written as a 5-dimensional SU2 gauge theory with 8 flavors, and the E8 flavor symmetry is going to become an affine E8 symmetry in the geometry. So we need to write down a geometry for this, and it can be written as follows. So SU2 with 8 flavor is 1 Hirzebruch surface, whose degree I'm choosing to be 1, with 8 blowups for the 8 flavors. And the affine E8 is going to be 9 non-compact P1 fibered surfaces, which I'm denoting from N1 to N8 and N0. Here the E curves are non-compact curves, gluing them together, and they have a compact fiber F, each of them. And now the gluing between them happens such that the fiber is glued to some curve here, which by Calabi-Yau condition should be a -2 curve. So you're looking for a set of -2 curves inside this F1, F18, which intersect with each other in the form of an affine E8 diagram. And these are these curves. Is F minus X1 minus X2 should go to the N4, E minus X1, and then you have X1 minus X2 up to X7 minus X8 in the rest of the trunk. Okay, so now I want to blow down. I want to remove a flavor and go to the theory SU2 with 7 flavor, which corresponds to blowing down one of the blowups on this. The only consistent blowdown is actually blowdown of X8. So when you blow it down, it leads to a flop transition. So what happens is that X7 minus X8 means that the blow of X8 was acting on X7. So when you blow it down, X7 minus X8 get converted into X7. And here by Calabi-Yau condition, there should be a -1 curve. So there is a blow up. The situation is like this: X7 minus X8 gets converted to X7, and there is a new blow up on the N0 on this non-compact surface N0s, such that F minus X is glued to X7. Okay, so now I want to carry out this blowdown for infinite. I want to completely carry out this blowdown. So I want to send the volume of this new blow up to infinity. I want to send the volume of X to infinity while preserving the volume of X7, since I want this matter content to be inside my theory. Since X7 is glued to F minus X, you see that the volume of X7 is actually the volume of the fiber of N0 minus the volume of X. And if you impose these two conditions, you find that the volume of the fiber goes to infinity. So this means that the N0 surface decouples from the flavor symmetry, and you're left with a set of surfaces N1 from N1 to N8, which form the Dinkin diagram of an E8 algebra. So the conclusion of this blowdown process is that the 5D SCFT, which can be described by SU2 with 7 flavor, has an E8 flavor symmetry, which is a well-known result. And then you can continue on and you will find SU2 plus 6 flavors has E7 symmetry and so on. And this type of analysis can be generalized to more complicated theories, but I leave these more complicated details to the paper. Right, so let me end. So throughout this talk, I have described some very simple situations I have illustrated all these applications by some very simple examples, but these examples can be generalized as much as you want. For instance, I looked at SU3 and SP2 gauge theories. You can look at even more complicated gauge algebras. You can look at G2, F4, E6, any kind of gauge algebra you want. I looked at very special matter content like the fundamental matter, but you can look at antisymmetric matter, symmetric matter, any kind of complicated matter you want using this setup, and you're not restricted to anything. So this geometric method allows you to uniformly study all sorts of examples and very complicated examples as well. The complicated examples have also been worked out, and the whole calculus of dealing with 5-dimensional systems and 6-dimensional systems compactified on S1 has been developed to study these kind of applications, has been developed in gory detail, which can be found. And so I'm going to close this talk with a pointer to literature, to my papers on this subject. So if you are interested in more details, so if you are interested in a detailed study of Calabi-Yau threefolds associated to 6-dimensional SCFTs on a circle, then please have a look at these 3 papers. And if you are interested uh, in producing 5D SCFTs from 6D SCFTs by integrating our BPS particles alone, and you want to understand detailed calculations of flops and blowdowns, you can have a look at this paper. And if you're interested in decoupling, the another way to produce 5D SCFTs, you can have a look at this paper. And if you're interested in dualities between 5D gauge theories, then please have a look at this paper. And if you're interested in knowing what the 5D and 6D SCFT UV completions of 5D gauge theory with a simple gauge algebra are, then they were recently worked out in this paper. And T-duality of little string theories and flavor symmetries of 5D SCFTs are going to appear soon. So yeah, so that finishes my talk.
All right, thank you very much.
I have a question. So,
Yeah.
Lakshya, can you go back to the slide where you presented the conjectures that all 5D CFTs can be obtained from 6D CFT on a circle? I couldn't remember the details. Yeah. Can you comment on how much mathematical evidence is there for the second line, for the second conjecture?
No, there isn't any mathematical evidence. It's still at a conjectural stage.
And I thought for elliptic fiber Calabi-Yau threefold, there are only finitely many topological types for elliptically fiber Calabi-Yau threefold.
So these are non-compact ones.
Oh, sorry. Yeah, sorry. I guess I was thinking about the compact ones. Yeah, sorry. Never mind. I see. I was wondering if your conjecture is true, does that shed any light on classification for Calabi-Yau threefolds?
You mean the compact ones?
Yeah, or yeah.
No, these statements are about non-compact ones because
Okay.
they're
Okay. Yeah. Understand. I see. Okay. Thank you.
I'm still curious about the meaning of this UV duality of 2 different IR theories with the same UV origin. If you take, say, SU5 and you hex it down to SU4 times U1, or to SU2 times SU3 times U1, will you, by your definition, are these 2 pairs dual to each other or not?
No, they're not.
And what's the difference between this and what you said?
So what I'm discussing is are only motions along the space of mass parameters and the Coulomb branch. I'm not going to Higgs. I'm not going to turn on webs for which correspond to Higgsing.
Well, you can always add a field. The parameter that you deform can be a field that you deform. So I don't see the conceptual difference between them.
If you the deformation parameters are mass parameters, so they are going to be Coulomb branch moduli for some non-dynamical fields. So I'm restricting myself only to Coulomb motions on the Coulomb branch of dynamical and non-dynamical fields, and not on the Higgs branch.
But moving to the Coulomb branch is Higgsing the gauge group to a smaller subgroup. It's not a Higgs branch, but it is Higgsing, right? So it's not so different from the example that Nati raised.
I want the moduli to all lie in the vector multiplets. So the ones I will give Web to will lie in some dynamical and non-dynamical vector multiplets. And the Higgs branch motions correspond to the ones which lie in the hypermultiplets. So they will be rotated by SU2R symmetry. So there is a difference. Right? I want to give webs to operators which are singlets under SU2R.
Yeah, I understand. Yeah.
Right.
Sorry, I was going to say, it sounds like more like you have a grand unified theory for all these SCFTs and not these analogy rather than a duality. But it's semantics, although it's not what we normally mean by the word duality. I think that's anyway.
Yeah, maybe the word duality is not nice. Yeah.
Sure. Any other questions for Lakshya? All right. If not, let's thank him either live or unlive for a very nice talk. Thank you.